to the 2024 Virtual Water Ambassadors Lunch and Learn webinar series. This is part of Martin County's Stormwater Education Program, along with UF-IFAS Extension and Florida Sea Grant. And so again, my name is Vincent Encomio, along with my partner in crime, Lisa Krimsky. And we're going to go ahead and get started. We've got a great webinar for you today. But before we get going, just want to remind you of our upcoming webinars in May, June, and July. We are at noon to 1 every third Tuesday of the month until through September. We will have an additional webinar in September, and right now that's looking like September 3rd, the Tuesday after Labor Day. So hopefully you guys will all be back at work and be able to join us for that. But take a look here. We're going to post the registration links in the chat for you guys to get pre-registered. And if you are unable to attend those webinars, we will post them on our UF-IFAS Extension Martin County YouTube channel. I'm currently up to date on our previous offerings from January through March. And once we get this recording processed, we will post this on that web link. Again, it'll probably take about a week or so before we get that up. But we also have our past recordings all the way going back to 2020. So if there's any other topics that you're interested in, go ahead and look through those playlists, and there's a lot of information in there. So we'll go ahead, just go through a few housekeeping items. We'll say if you have any questions, feel free to enter those into the chat at any time, but we will wait until the end of our webinar. Our speakers are done to address those questions, but feel free to enter them at any time during the webinar. And with that, I'd like to introduce Drs. Kelly Kibler and Melinda Donnelly. Dr. Kibler is an associate professor of water resources engineering in the Department of Civil, Environmental, and Construction Engineering at the University of Central Florida. Oh, I made it through that. She's the faculty of UCF's National Center for Integrated Coastal Research and a faculty fellow of UCF's Center for Global Economic and Environmental Opportunity. Dr. Kibler's laboratory conducts interdisciplinary research at the crossroads of water resources, engineering, and aquatic ecology. And she's applying her work to the design of natural infrastructure used to protect communities from climate hazards such as erosion and flooding. And that'll be the main topic of their talk today. Dr. Melinda Donnelly is an assistant research professor in the biology department at the University of Central Florida, with a joint appointment with the Sustainable Coastal Systems Faculty Cluster Initiative. She received her PhD in conservation biology from the University of Central Florida, and completed a postdoctoral position there as well, looking at the social and ecological impacts of estuarine restoration in Florida. And they're very active in oyster and living shoreline restoration in the northern part of the Indian River Lagoon. And her research is focused on estuarine habitat restoration and ecology, including wetlands, oysters, and seagrass in Florida. So with that, we're very pleased to have both you get a twofer today. You get Dr. Kibler and Donnelly today. And so we're very pleased to have them. And this is going to be a great webinar. And so I'm going to, Kelly and Melinda, I'm going to go ahead and stop sharing so you guys can go ahead and put your presentation up.
All right, everybody good? All right, guys. So thank you for having us on today. We're very excited to share with you a project that we've been working on for quite a while now. When I was putting this together, I realized we actually started our first round of shoreline assessments back in 2015. So going on 10 years of putting all of this together. So very excited to be able to share some of the results that we found, kind of what the purpose of the project is, and then really focus in on the overall application of all of this information that we've been gathering and how we can help improve restoration and the use of green infrastructure throughout Florida. All right, guys, with that, so I'm going to be providing you sort of the introduction into the project and then the methods and results from some of our shoreline characterization. Then I will pass it over to Kelly to talk about the hydrodynamic modeling, and then we'll talk kind of at the end about how we put all of that together. Now, the focus of today's talk and this research is really taking a look at shorelines. And when we think of shorelines in the estuarine system, they really do represent this sort of interface, and in many cases where sort of nature and the human element start to overlap. So if you think of kind of an average shoreline, throughout the Indian River Lagoon, we have that connection between the greater water body and the aquatic subtidal habitats coming into connection with those intertidal habitats like our wetlands and oysters, and then often leading into the terrestrial side. And for many of these locations, this terrestrial component represents this connection with our human communities. Now, when we think about the importance of shorelines, we can understand why there's so much focus on restoring these areas, as well as conserving those areas that are still natural. Now, when we think of a natural shoreline, these are areas that tend to have a combination of habitats. We're making that transition from the terrestrial into the intertidal and then going into subtidal. So we often have this combination of, say, wetland vegetation, things like our mangroves and other plants that are able to live in that nice, wet, salty environment. Oftentimes in the lower intertidal zone, we'll have our fringe oyster reefs, or what I've been finding quite a lot of down in the southern part of the Indian River Lagoon, the oysters actually living on the roots of the mangroves, kind of creating this complex of both wetland and oyster habitat coming together. And then in a nice healthy estuary where we have good water clarity conditions, we can see seagrass often growing immediately adjacent to those intertidal reefs in that subtidal zone. So we create this sort of complex matrix of habitats, and for many of our estuarine species actually utilize all three of these habitats on a daily cycle, if say they're moving back and forth through them in order to find food, or maybe at different parts of their life cycle. So say using seagrass for their larval or juvenile stages, and then maybe getting larger and making their way into the oyster reefs or the wetlands. So maintaining this connection between these habitats is really critical for supporting all the biodiversity. It also is going to help increase the overall number of ecosystem services that we're going to be getting from these estuarine habitats. So when we think of ecosystem services, these are all the sort of benefits that we as humans tend to gain from simply having these natural systems present. And so when we have this combination of shoreline vegetation and our oyster reefs and our seagrass, we are really maximizing the number of ecosystem services that we would expect to get within these areas. So one of the big advantages of maintaining these sorts of habitats on our shorelines is that they all tend to provide shoreline protection. They help to break down that wave energy that can lead to erosion and keep all that sediment in place, which is important for maintaining that water clarity and reducing the amount of sediments that are going to be kind of moving around in the water column. They also provide really critical habitat for a variety of different species, including a lot of species that are economically beneficial for commercial or recreational fisheries, including things like our blue crabs and our iconic redfish here in the Indian River Lagoon that everybody loves to come. We also see this overlap with what we may consider more of our upland terrestrial species. So many different bird species utilizing those shoreline habitats for foraging or nesting, as well as some of our mammals, everything from deer to raccoons to bobcats, making their way down to the shoreline. So supports lots of biodiversity when we have these combined habitats present on the shoreline. We also see improved water conditions when these habitats are present. So all three of our shoreline habitats, seagrass, oysters, and our vegetation help to filter out the water. The plants can do this through the absorption of nutrients for their own plant growth. Many of our wetland plants also can absorb things like pollutants, as well as prevent some of our larger pieces of plastic from making their way into the estuary. Our oysters are filter feeding animals, so they're going to help improve that water quality by taking out all of those particles that are moving through the water and help to reduce some of the negative effects that come from some of our algae blooms. They're also going to play an important role in nutrient cycling, making sure that too many nutrients don't remain in the water column as fuel for some of those algal blooms. We've also come to recognize their importance in terms of carbon sequestration, allowing for large amounts of carbon to actually be stored within these systems as well as below ground, helping to reduce the negative effects of that carbon dioxide in the atmosphere, and a variety of economic benefits from the support of commercially and recreationally important organisms to improving the overall quality of the area to support ecotourism. Now, unfortunately, despite all of these benefits that we've seen, we have seen this very significant loss of estuarine habitats. And this is something that's obviously happening here in the Indian River Lagoon, as well as across Florida and really around the world. Now, these loss of habitats have been occurring for a variety of different reasons. All right. One of the big negative effects that we've seen along our shorelines is a lot of development and loss of those natural habitats for infrastructure. So things like our stormwater drainage, coming directly into the lagoon from all of those adjacent areas, rather than being filtered through the wetland and allowing those sort of natural filtration properties to take effect. We've also seen with this development kind of a change in what our shorelines habitats look like, going from things like our turf grass, which often necessitates a lot of things like pesticides and fertilizers, which end up washing into the lagoon system, as well as a change in that shoreline characteristic. And the picture that you guys see here, a steeper shoreline that is kind of covered in these large boulders, what we would refer to as a hardened slope. Now, all of these changes within our estuary has led to a decline in water quality. As we see more stormwater coming into the lagoon, this is bringing a variety of nutrients, a variety of pollutants, as well as sediment and debris from our terrestrial areas. This increases the nutrient load within our estuaries and can increase the likelihood of algal blooms like the brown tide that we had up more on my end of the lagoon a few years ago up in the Banana River and Mosquito Lagoon region. Now, guys, all of these things are basically linked together, right? As we start losing our habitats and we start losing all of those ecosystem services like stabilization and water filtration, we see this kind of decline in water quality. And as that water quality is declining, whether it's from increased inputs from stormwater, triggering algal blooms, or say increased erosion, increasing the amount of sediment that's coming into the water, this ends up having cascading effects throughout the lagoon, leading to things like our seagrass loss due to them not being able to access the sunlight that they need in order to grow. Now, guys, the main issue that we're going to be focusing on as part of this project is the hard armoring of shorelines. Now, this is basically occurs whenever we remove our natural habitats, so our wetlands, our oysters, and our seagrass, and instead replace it with some sort of hard structure. So this is usually associated with either human infrastructure or human development as a way of protecting kind of those human resources that are going to be on the landward side. Now, this hard armoring of shorelines has been recognized as a significant threat to estuarine wildlife by the Florida Fish and Wildlife Conservation Commission. And we've seen a decline in this critical habitat that supports all of the biodiversity in the lagoon, threatening the continued populations of those species that are so reliant on those habitats for their nursery, breeding, and foraging grounds. We also are going to see this loss of ecosystem services from natural shoreline habitats. So when we think about the extent of a lot of this hard armoring and decline of our natural systems, it's not a surprise that we're also seeing this decline in water quality as we're no longer benefiting from those natural services that we would be getting from those natural systems. Now, guys, one of the ways that has become popular over kind of the past decade or so to address this issue of hard armoring is what we refer to as living shorelines. Now, living shorelines, kind of in direct contrast to our hard armoring, are often referred to as soft armoring. And what this means is that we're using native and natural materials to decrease erosion and increase our shoreline habitats. So whereas our hard armoring usually has one purpose, that's just to stabilize the shoreline and protect that area from erosion, our living shorelines can help decrease erosion as well as provide us, with this really important habitat that is on the decline, throughout Florida. Now, this is a restoration method that we refer to as biomimicry. So bio meaning living and mimicry meaning, basically copying. So what we're doing in this case is basically copying what we see on natural shorelines. So for example, we may find a natural shoreline that has our kind of oysters down in the lower intertidal, and then our salt marsh grasses and mangroves in the middle to upper intertidal zone. Now, we can basically replicate this on eroding shorelines using these native materials, native plants. So we have our grasses and our mangroves here, and using oyster materials to create a breakwater to help reduce that wave energy and allow those plants to kind of grow in so that we're getting that multi-habitat and sort of multiple layers against that erosion, helping to keep all that sediment in place and reduce that wave energy. Now, guys, if we think of the benefits of the living shoreline stabilization, obviously one of the big things that we need in this case is to reduce erosion. And so most of the shorelines that we're going to be looking at in terms of using this type of method are going to be those that are actively, showing some sort of an erosion effect. Now, the benefit here is that we're not only going to stop erosion like we do with our hard armoring, but we're also going to get additional benefits out of using this type of method. So one of the biggest ones is that we get to recover those ecosystem services. So everything from increased area of habitat, replacing all of that nice wetland vegetation or the oyster reefs within that area, also bringing back the water filtration, the nutrient cycling that's going to help improve the water clarity and water quality throughout the estuary. Another benefit is that they do have a natural appearance. The location that I started this work in was actually in Canaveral National Seashore up in Volusia County. And this was really important for the national park to maintain the natural appearance. When you're kayaking or fishing through the national park, you don't want to look at a bunch of boulders or a concrete seawall and things like that. A new benefit that is becoming more important as we think of kind of making our areas more resilient to future changes is that these living shorelines have the ability to adapt to sea level rise. So whereas a seawall is kind of always going to be static, it has a maximum height that it's never going to be able to go beyond. Things like oysters and our coastal wetlands are actually able to keep up with sea level rise as long as it's not happening too rapidly through that accretion of sediment by stabilizing that area. So we get some long-term benefits of maintaining this habitat as well and making our areas more resilient to those future changes. Now, guys, as great as living shorelines are, and this is something that I've spent a lot of time doing, so I can attest to the fact that they do work very well. In many cases, we do see failure of projects. And the main thing that we've identified over time by looking at both good and bad living shorelines is that a lot of these projects tend to fail due to poor site selection. A lot of projects will just simply go out, like the one that you guys see here, and plant a bunch of mangroves along the shoreline. Well, the problem is if that area is not suitable for mangrove planting, well, we're not really getting any benefit, right? And we end up losing those mangroves. And in the end, this ends up resulting in a loss of resources, right? There is plants grown multiple years in this cases to put out. There's a lot of time that goes into these sorts of restoration projects. There's a lot of funding that comes from many different sources. And in the end, I think most kind of the biggest negative effect that we see just in terms of support for these projects overall is the loss of public support, right? Nobody wants to go out and see an area where your taxpayer dollars were invested in planting a bunch of mangroves only to see all of the mangroves lost. So anytime we have this, a failure of a project, we see these kind of losses across the board, resulting in negative effects both to the habitat as well as sort of the community perception and support of future projects, reducing the likelihood that people may want to actually, invest in those in the future. Now, this is the problem that Kelly and I have been trying to address and through the project that we're going to be sharing with you guys today. Now, the first part of this is to understand our shoreline. And this is really important for making sure that our site selection is going to be good. So we first go out and evaluate sort of the current biological and physical characteristics of the shorelines. As the biologist, my focus is on the shoreline characterization, and I'll share those methods with you in a moment, looking at sort of the biological characteristics of the habitat and some of those site-specific characteristics that are driving those. The hydrodynamic modeling is Kelly's specialty, and she'll be sharing the methods and what we found so far in some of the other areas that we've applied this. And then basically, we're going to combine that data together. So we're going to develop tools based on the data that we're developing that will prioritize restoration efforts and identify best methods for stabilization. So this gives resource managers sort of a multi-step approach to take a look at their site and hopefully figure out what the best options are for that location, increasing the likelihood that we're going to end up with a nice, successful living shoreline like you guys see here, reducing the likelihood that we're just going to end up with a bunch of, sticks and washed out mangroves, which nobody's going to be happy to see. Now, guys, the first part of this is the shoreline characterization, and we do this basically, I'd like to think of it as a sort of rapid assessment at a relatively small scale. So we collect data along transects at about 30 to 100 meter intervals along the shoreline. 30 meters is sort of our minimum, usually taking into account sort of small scale changes like what you guys would see along a developed shoreline. In some locations, we have relatively consistent conditions. So if you think of a natural shoreline or a mosquito impoundment that tends to have very standard conditions, we can go a little bit further knowing that we're sort of capturing the full characterization of that site. Now, at each of these locations, we record a variety of abiotic and biotic parameters. This includes the presence of hard armoring and the type, the adjacent property use, whether it's natural, roadway, somebody's home. We do the slope of the shoreline so that we can get a feel for how quickly we're transitioning from that terrestrial to subtidal zone. We do the width of each habitat or structure so that we can develop estimates of how much mangrove area we have along the shoreline. We identify all of our plants to species, record the presence of oysters and seagrass in that location, as well as evaluate the severity of erosion. And in addition to these characteristics, we also will record the location of outfalls. So we're also getting a feel for how many locations do we have sort of water coming in from those adjacent areas and where they're going to be located so that we can kind of take that into account when we do the full assessment of the sort of status of that particular shoreline area. Now, as I mentioned, we started this work back in 2015, starting in a relatively small project in the city of Titusville up in Brevard County on the north part of our Indian River Lagoon system. This included 18 total miles along the Indian River. Now, that part of the project got a lot of attention, and Brevard County, when they heard about it, actually wanted us to expand it throughout their entire county. So from 2016 to 2017, we went around all of Brevard County and completed 200 miles in the North Indian River and Banana River. And after that, we expanded it north into Mosquito Lagoon, incorporating some of those federally managed lands that were not originally incorporated in the Brevard County focus there around NASA and Merritt Island Wildlife Refuge and Canaveral National Seashore. And this gave us another 156 miles, completing all of Mosquito Lagoon and finishing off that north part of the Indian River system. So we had kind of the whole coverage in the northern part of the Indian River Lagoon from Ponce Inlet to Sebastian Inlet, Inlet, and we had a total of 11,000 total transects. So lots of information for us to use kind of going into sort of those next stages of creating the models. Now, as we shared this information throughout a variety of local restoration meetings, we got the attention of Jennifer Baez and Beth Orlando from the Palm Beach County Department of Environmental Resources Management, and they were interested in expanding the shoreline characterization down into Palm Beach County, specifically focusing on the Lake Worth Lagoon. Now, this actually got started right before COVID hit in 2020. So I think Beth spent a decent amount of time of 2020 kind of going out isolated, collecting this data, giving her a break from, sitting through all of these online meetings and working from home like all of us did during that time frame. Now, this part added additional 86 miles to the total area that was evaluated. They also got about little over 1,200 data points. So again, really providing a lot of information for these sites. Now, guys, our most recent project has been basically filling in the gaps. So we had everything from Ponce Inlet to Sebastian Inlet to the north, and then we had Lake Worth Lagoon down south. So myself and Kelly, as well as Vincent, received some funding from the NOAA grant in order to fill in this gap, allowing us to focus in on the area between Sebastian Inlet and Jupiter Inlet so that we can have this nice kind of consistent coverage of our shoreline characterization. So this project now has been going on for about 1.5 years. We've been making good progress evaluating this area. We currently have 130 miles completed with an estimated, I'm going to say about 70 miles probably left to go. We realized that our Indian River County area in particular had quite a lot of shoreline with all of their islands and kind of, back and forth wavy parts of the shoreline. So we definitely may have underestimated a bit what we thought we were going to get. Now, currently, we do have 100% of Indian River County completed. We've got a good amount of our St. Lucie County done, estimated to be about 60% completed, with a few extra miles completed by myself yesterday with some community volunteers. And our next big focus is going to be kind of moving down in the southernmost region, down in Martin County. Currently, we only have about 5% of that area completed. However, starting in May, this area is going to become our big focus. So I am working with Vincent to get some days scheduled to have some community volunteers to come out and help us collect that data. So if you guys are interested in that, we'll work with Vincent to make sure we can share those dates with all of you guys if you want to come out and see what this shoreline characterization looks like in person. Now, guys, just to kind of give you an idea of what this data looks like when we start putting it all together, I'm just going to quickly share with you some results from the Lake Worth Lagoon assessment, and then I'm going to hand this over to Kelly for some hydrodynamic information. So, guys, when we think about our Lake Worth Lagoon, we do see a significant amount of this area did have what we classified as our hardened shoreline. We had about 68% total shoreline hardened, with the majority of that being part of our sort of bulkhead and seawall classification, and a smaller percentage, only about 11%, what we refer to as hardened slope, where we're using some sort of boulders, rocks, rubble. We've seen pretty much everything used on this hardened slope type of shoreline. Now, guys, the big changes here in terms of the conditions is that our bulkheads tend to have minimal erosion. So that's kind of, they are doing their job in terms of our stabilization. However, most of these are associated with heavily developed areas. So we end up with a lot of ornamental vegetation, or in many cases, just like a sidewalk or something like that behind. So we end up losing that connection between the terrestrial area and the aquatic zones with the presence of these bulkheads and seawalls, where we're basically sort of cutting that area off and reducing that, nice transition and habitat mosaic that we see on our natural shorelines. Now, for a hardened slope, about 25% of these had moderate to severe erosion. So even with those harder structures and boulders on the shoreline, we do still see evidence of erosion within those. Most of those also have a very steep slope with a very limited intertidal width. So even though we would potentially see oysters down at the bottom part of the rock, the area that they were able to kind of exist in as intertidal zone was very limited. So again, kind of losing that connection between our terrestrial and aquatic habitats. Now, guys, in terms of areas without armoring, we did find 32% of the lagoon was not armored. About 1% fell into these kind of open sandy shorelines, often associated with things like spoil islands or something along those lines. And about 29% fell into what we would consider kind of our more natural vegetated shoreline. Now, in areas where we did see our wetland vegetation, these areas did tend to be very stable. So we had minimal erosion. The slope is very low, allowing for that, nice transition from subtidal up into the terrestrial area. We do tend to have a wide intertidal zone, in some cases over 10 meters, allowing for this, again, kind of nice wide intertidal habitat filled with mangroves. And in this area, quite a lot of oysters in those kind of lower to middle zones, providing that connected habitat that we would associate with our more natural shorelines. All right, guys. So with that, I am going to kind of hand over the talking to Kelly and let her talk to you about the hydrodynamic modeling. And I'm going to be forwarding her slides, so you will hear her say next slide as we go through.
Thanks so much, Melinda. So the next part of the characterization was to do some modeling to try to characterize some of the potentially erosive hydrodynamic forces that might be impacting the shoreline. So what you're going to see is that our hydrodynamic modeling kind of does double duty. So this first objective is still, we're in the characterization mode. So our methods, we divided up all of the areas that Melinda has introduced into various modeling domains so that we could change boundary conditions, as the depth profiles and water levels change. We wanted to be able to capture that in the modeling. And over these 5 different study domains in the Indian River Lagoon and Lake Worth Lagoon, we ran a stationary runs of the simulating waves near shore, or SWAN model, on a high performance computing cluster. So we ran about thousands of different combinations of wind speed, direction, water level, over a 70-meter model resolution within each of these domains. And some of our model post-processing involved the integration of those modeled wave heights with a 45-year wind record so that we could take that long-term wind record and transpose that into a long-term wave climate. So probabilistic wave climate, understanding how large the waves are, how often. Next slide, please. So some of that variability in boundary conditions and forcing conditions can be seen, if we look at just some wave models results from Mosquito Lagoon. On the left-hand side, these would be a 50th percentile or median wave height, so the height of waves that are exceeded 50% of the time when the water level is typical, so the median water level. And then on the right-hand side, these would be the slightly higher waves that would happen if we look at 80th percentile wave heights. So the wave height that's being exceeded 20% of the time when the water level is high. Next slide, please. We are still working on the wave modeling across all of the 5 different study domains, but just here's a few preliminary results about how wave heights, this is the 80th percentile wave height generated over a median water level in each of the 5 different study domains. Next slide, please. So we did validate our modeling. We established 4 different monitoring stations across the study domain. So one station in Volusia County, and we're looking at some data from Volusia County here. Another in Brevard, one in Indian River, and one in Palm Beach County. And those 2 remaining Indian River and Palm Beach County stations are up and running right now with various degrees of success. But what we do is we use these measured wave data to compare to our simulations to understand how well our model is working. So here we're looking at the wave climate across various wave percentiles. That black line is our modeling, and then our observed data are in those purple and blue lines. And next slide, please. And what we find is that our model has a really hard time of producing small waves. So this area where our model is really just underperforming our observations, this is where our wave height falls below 2 centimeters. There just really isn't a wave model that I know of that can reproduce ripples like this. But once we get into, slightly larger waves, we see more fidelity within our modeling. Next slide, please. So above 2 centimeters, we can conclude that our model is doing a reasonably good job of reproducing the wave height. Next slide. And I want to draw your attention to this point right here where the arrow is pointing. This is our 80th percentile wave height. So again, this is the wave height that's going to be exceeded 20% of the time. And in this particular location that has a pretty low fetch, we see that that 80th percentile wave height is just over 5 centimeters, so relatively small waves here. The 80th percentile wave height, what we found is that it encapsulates a lot of information. So that is the wave statistic that we're going to be using as we get a little bit further into the analysis. So just want to show you where that comes from. Next slide, please. So we've characterized now potentially erosive forces through the hydrodynamic modeling at a resolution of 70 meters along all of the shorelines that Melinda has presented. But we're still missing some really vital information, and that's because, you know, this can tell us about potentially erosive forces, but different shorelines are going to have different resistivities to erosion. It really just depends on what is on that shoreline. You know, so we could have the same hydrodynamic signature on 2 different shorelines, and one may erode and the other may not, because the 2 shorelines have different resistivities to that force. So what are the main parameters that we're looking at that are going to tell us about resistivity or resilience of a given shoreline? One is the gradient. So the intertidal slope and near subtidal slope. So for instance, the top left, we've got this low gradient bare sediment shoreline that maybe is not eroding, but then next door, there's a more high gradient bare sediment shoreline that is eroding. As Melinda pointed out, when we've got natural wetland shorelines with a low slope that support vegetation, unlikely to see erosion on a shoreline that looks like that. So that's the next thing that we're going to try to do, is represent how resistive a given shoreline may be to erosion given a hydrodynamic signature that we've modeled. Next slide, please. So we can also apply this kind of thinking to stabilization techniques. So different stabilization techniques may also have variable resistivities to erosive forces. How much strength or armoring do we need in going from that spectrum of a completely hardened gray infrastructure like a revetment, as opposed to moving to a completely green and soft armoring technique like vegetation only? The real problem with trying to design a good, robust living shoreline is matching the correct method or the correct materials to address the potential erosion problems at the site scale. Next slide, please. And especially when we start getting into wanting to use living materials in our designs, you know, and there are a ton of reasons that we might want to include living materials that Melinda has gone over. But the truth is that we just don't have a great characterization for living materials and how resistive they may be to erosion. That type of material properties that we may have for concrete or rebar, it just doesn't really exist for living materials yet. So that's what we're trying to do. This is the way that we're going to make our hydrodynamic modeling data and all of this very rich shoreline characterization data that Melinda's team has collected work in double duty to try and figure out what are the hydrodynamic tolerances of some of these species that we might like to include as ecosystem engineers in living shoreline designs. So emergent vegetation, submerged vegetation, shellfish would be examples. Next slide, please. And so I'm going to go through an example of how we were able to characterize hydrodynamic thresholds for one type of emergent vegetation for mangrove species. So this was published a few years ago, and this figure is just introducing some of the main parameters that we're going to look at. The far left, this is that 80th percentile wave height based on the modeling, and you can see how it distributes itself over the study area that we're looking at. The shoreline gradient, so slope going from low slope in blue to higher slopes in red. The severity of erosion, so being characterized as either very, very severe, where the observed erosion at the time of shoreline survey is exceeding 30 centimeters in height, moderate erosion, kind of over 8 centimeters, but not quite 30 yet, and then very little erosion being characterized as less than 8 centimeters. And then the final panel is whether or not mature mangrove vegetation is present on the shoreline. Next slide, please. So just even looking at presence of mangrove and shoreline erosion can tell us a lot, right? Just if we have a shoreline that doesn't have mangrove vegetation, what we have found is that there is not a very big chance that the erosion is minor. There's a much larger probability of finding that severe erosion category when there are no mangrove present. Then when we look at our shorelines with mangroves, it's much more likely that we're falling into that minor or moderate erosion category. Next slide, please. So if we look at all of the wave climate from every shoreline that has been surveyed by Melinda's team, and we can see that there's a clear separation between the sites that have mangrove vegetation present and those that don't. And so I'm showing you here the 80th percentile wave height. So what we see is that mangrove vegetation becomes increasingly likely to find on shorelines when the wave height exceeds the 8 centimeter threshold, no more than 20% of the time. So as that 80th percentile wave height goes above 8 centimeters, it's less and less likely that we see mangrove vegetation. Next slide, please. So these are the same data just shown in a different way so that you can see the two distributions of shorelines that either have mangrove shown in blue, I'm sorry, in green, and those that don't have any mangrove vegetation shown in red. And while there is a good bit of overlap between these two distributions, there's also a definable separation that we can quantify statistically using a best fit of a logistic function between these two probabilities. So we can really pinpoint that moment in time, that wave height where it's 50% likely to find mangrove vegetation. So the probability of finding mangrove vegetation is equally likely as it is unlikely. So if we repeat this analysis over and over again at multiple different wave percentiles, so multiple points within our wave climate, we can actually get to the point where we can predict mangrove presence or absence based on hydrodynamic climate alone. Next slide, please. And so that's what you can see here. So on the x-axis, we've got the wave percentile, and then on the y-axis is the height. And as we get kind of towards the bottom right of this figure, this is where it is very, very likely that mangroves are likely to persist. Whereas we get more up into that upper left-hand corner, that's where mangrove are going to be more unlikely to persist. Next slide, please. And then we started just getting a little bit, playing around with another variable. What if we add another variable to this analysis and we add slope? How does the effect of a variable slope change this outcome? When we add slope in here, what we can see is that lower slopes increase the tolerance for hydrodynamic energy. So a mangrove is less likely to be eroded away by high wave energy if the slope is low, because there's just less energy available to move sediments around the mangrove roots. And so they're able to persist in a higher wave climate. And the opposite can be said too, that a high slope, even in a more moderate wave climate, can be more detrimental. Next slide, please. We also can use the locations of hardened shorelines within this kind of multivariate analysis. For instance, to be able to identify areas of shorelines that currently have some sort of armored or hardened structure on them, but maybe, these data suggest there are a few sites that we could remove that armored habitat, replace it with vegetation like mangrove, and it probably would do okay. So anywhere you see black points kind of falling into the big cloud of green points, it may be a reasonable thing to assume that some of these hardened shorelines could be replaced with a living shoreline containing mangrove. All right, next slide, please. So a couple of years after we published this hydrodynamic threshold, we got a really nice surprise, which was maybe an independent validation of our modeling methods. So researchers from Switzerland, UK, and Seychelles published a study where they used different methods in a different geography on different mangrove species to try to estimate the same thing that we had done. And they got really similar results. So they identified a mangrove wave threshold of the 80th percentile wave height of around 6 centimeters. Ours was 8. As you could see, the difference in slope could be the thing that makes the difference of 2 centimeters easily. So, I mean, in terms of science, it doesn't really get much better than this if you have 2 independent lines of inquiry asking a question and using different methods and coming up with a similar answer. So that gave us a lot of confidence that this methodology of being able to really couple together the assessment and shoreline characterization data with the hydrodynamic modeling is really pointing us in a good direction for assessing some of the flow ecology relationships for these ecosystem engineers that we're interested in. So we're currently working on trying to do this for more species. So we're looking at submerged aquatic vegetation right now, as well as oyster, both of which are a little bit different from mangrove, not being emergent species. So we're having to introduce new multivariate ideas of things like depth. But really promising preliminary results are coming out that we're hoping we'll be able to utilize so that we'll have kind of this full suite of understanding of where different species might be appropriate to use in living shoreline restorations. Next slide, please. So I don't know if, is this you, Melinda?
Yep, sorry, I realized I did not unmute myself, so I apologize for that. So I'll jump back in here. I'm going to give you just a quick overview of kind of how we put all of this together for prioritization, and then I will pass back over to Kelly to kind of wrap up with how we are using her hydrodynamic modeling of the species to take a look at what is going to be our appropriate areas. So for one of the ways that we can use all this data that we gathered is to take a look at how we can use shoreline conditions to prioritize our restoration efforts. So what you guys see here is a figure from the Cannon et al. Publication that Kelly mentioned, taking some of our shoreline characteristics and using it to sort of create sort of this almost like stoplight approach to where our most urgent needs for restoration are going to be. So this took into account the presence of shoreline structure, so whether it was a hard armoring structure or whether there was the presence of wetland vegetation like mangroves. It also took into account the slope of the intertidal zone as well as erosion severity. And we created kind of these 5 categories here to allow us to identify which shorelines were going to be in most need of restoration. And so the way that this worked was basically creating an algorithm that would allow us to identify shorelines that are currently stabilized, where we don't expect restoration to be needed. This would include things like our hardened shoreline. So as long as there was functional hard armoring there and no evidence of erosion, we are assuming at this point that that area is stabilized and restoration is not a priority. Now, as Kelly mentioned, these areas could potentially fall into locations where a living shoreline could be appropriate. So if we do have interest from the landowners in converting that hardened shoreline to a living shoreline, that is kind of another consideration that we can incorporate into sort of the model predictions. The other shoreline where stabilization is good would be our wetland shorelines, where we have the presence of that vegetation, a relatively low slope, and no evidence of active eroding. Now, the other 3 categories are going to be where restoration potentially either could be applied or may need to be applied, depending on the severity of the shoreline conditions. So our vulnerable shoreline would be areas where wetland vegetation is present, but it either has a moderate to steep slope or moderate to severe erosion. So basically, it doesn't have both. So we see some evidence of the potential for that wetland vegetation to be lost in the future. So it's definitely an area where we may want to kind of keep an eye on it or do some sort of preventative measures if that area is of interest. Our priority shoreline is kind of falling into our middle category for potential restoration, which either contains no wetland vegetation or contains wetland vegetation, but has a moderate to steep slope or moderate to severe erosion. And these areas would be expected to deteriorate further in the future without restoration. So again, a good one to kind of come in preemptively before we lose everything or see evidence of severe erosion to stop any further loss of that area. The last category would be sort of the highest priority in terms of needing restoration. Our urgent shoreline has basically no wetland structure there whatsoever. We've lost all of the wetland vegetation, and there is evidence of moderate to severe erosion. So this would be kind of our area that we could highlight for resource managers that would be most in need of immediate restoration to prevent any sort of further degradation of that location. All right, and I will switch back to Kelly for kind of the last part for the mangrove survival probability and how we can combine that with our prioritization.
Right. So once the prioritization model has identified for resource managers the places where resources should be directed and focused, the next question is, well, okay, what is the method that's going to work at the site scale? And that's where, you know, some of the flow ecology relationships can come in to inform which ecosystem engineering species are going to be a good fit at the site scale. And something else to keep in mind is that just because a mature mangrove forest or a fully mature and stable seagrass bed could exist within a given hydrodynamic condition, that doesn't necessarily mean that it's going to be stable from day one. So an analysis like this could help us identify places where some of these more hybrid gray to green techniques might be useful in trying to get restoration to be successful in those early days when things are a little bit more vulnerable. Next slide. All right, so I think that is going to then wrap up our talk. So I've put in some links here where you can go to either view on like a GIS story map all of the data that we've presented today. We're in the process of updating this as we do more and more miles of shoreline along the project, but at least a few of the counties we presented today are on this GIS story map. And then if you actually want to download those data and use them like in a GIS shapefile, you can also do that. I've given you the link of where you can find it. If you have any questions for Melinda and I, there's our contact information, and I think we would be happy to take some questions.
Thank you so much, Kelly and Melinda. Melinda, could I ask you a quick question, a quick favor? Could you copy and paste those links into the chat?
Yes.
All right, thank you so much.
And
let me see, we've got going through the chat here. Thank you so much for covering all that, and I posted in the chat, but as Melinda had mentioned, we'll be working in Martin County sometime soon. So please reach out to me if you are interested in helping us apply the shoreline characterization method to remaining areas in Martin County. So the first question I have here, really, I guess yeah, it is a question from Bill. He writes, you studied 18 miles of shoreline in Titusville. Would you be willing to restudy this 18 miles because there has been great devastation of the shoreline and major pollution increases that has caused a major manatee die-off and loss of all seagrasses in 2021? I'm not sure if the pollution can be addressed, but you know, if
yeah, I can say that we found quite a lot of stormwater outfalls and random people's backyard outfalls and things like that were coming when we were doing the Titusville site. So I can only imagine that there's a lot of input from the different locations. I'm definitely interested. I actually live in Titusville, so that area is kind of a personal favorite of mine. I'm actually working right now on a proposal to do some hurricane assessments of some shorelines in Canaveral National Seashore. So maybe we could somehow work the Titusville area into that as well.
Great. Awesome. And is there are there some living shoreline efforts ongoing in Titusville at this time?
Yes, there are a couple different locations. The big one that's become the focus is the causeway. Unfortunately, we did find that quite a lot of the Titusville shoreline is already hard armored and has a lot of infrastructure associated with it. So converting over to living shorelines has been a little bit slow in that area due to just concerns that it's not going to provide enough protection for some of those sorts of things.
Okay, great. Thank you. Mike comments, and just to sweeten the deal for if anybody wanting to volunteer with us, he will buy the crew lunch in Jensen Beach if we are doing the shoreline characterization at the Environmental Study Center. Thank you, Mike. Mike works at the Environmental Study Center, and he and Carly Batts of Martin County and the Environmental Study Center had actually done completed a living shoreline with shoreline plantings. So it's good timing to apply the methodology there, I think, at this time. So thanks, Mike.
Yeah, thank you. We'll definitely plan a day there.
Okay, cool. And I have a question with the instrumentation and maybe the modeling. Can the waves from boat wakes versus wind-driven waves be distinguished?
Thank you for asking that question, Vincent. Melinda, can I trouble you too much to put up the last couple of slides? I kind of had prepared for somebody to ask this question. It's a good one because the model that we have used to characterize hydrodynamics is specific to wind-driven waves. But waves from boat wakes can be incredibly erosive. So this is just a time series of data of one afternoon. My lab and I were out. It happened to be maybe a weekend day or something like that. And we were doing a hydrodynamic monitoring experiment in Mosquito Lagoon. And we were purposely trying to avoid boat wakes because they're really difficult for us to deal with in our data. But as you can see, that was a lost cause. So the red circles indicate the peak of passing boat wakes. And then the green circled areas, this is the ambient condition. So potential for erosion from hydrodynamic forces is going to be a function of the magnitude of the force and then the frequency. So you can see we've got both going on here. We've got high magnitude events happening at a high frequency, which is going to translate into lots of erosion. So next slide, please. The SWAN model has no way of generating boat wakes, and actually generating a model for boat wakes is incredibly difficult. There are so many variables. How close is the boat to the shoreline when it passes? Was it on plane? Was the shape of the hull a V-hull or was it a skiff? Was it moving at a high rate of speed? There are just so many different variables that have to be captured to accurately model magnitude and frequency of boat wakes. So what we did is we took frequency coming from boat traffic data, combined that with the potential magnitude that comes from speed zonation, put them together to have a combined risk factor, and then estimated areas of shoreline that were at high risk of being impacted by boat wakes. And what we did is we took those out, the areas that were the highest risk, we took those out of our flow ecology relationship development. The outcome wave height thresholds that come out of that work are still going to apply to boat wakes, but we can't include areas that are potentially affected by boat wakes in our modeling and in the flow ecology relationship development because they're not captured well in our hydrodynamic modeling. So really good question, Vincent. So the answer is yes, we're thinking about it, but no, our model, the SWAN model, cannot model boat wakes. And if anyone has a good model that can estimate boat wakes, please let me know.
Great, thank you. So the next question we have here is from Mary. how polluted is the water you are working with? Excuse me, sorry about that.
I mean, it varies a lot based on our location. We've been doing a lot of stuff around, the inlets in Sebastian Inlet and around Fort Pierce Inlet here as of late, and that water has been looking very clear and very nice. We do notice when we get closer to the rivers or the areas that have the canals on the, mainland side that you do tend to see a lot more sediment in the water. There also is a lot more just, algae and things like that growing on the rocks within those regions, which usually is an indication to us that there is a lot of nutrients coming out of those locations, just due to the thick algae growing on the rocks. So I would say it's been pretty variable depending on location, with some areas definitely looking better than others.
Thanks, Melinda. We've got another volunteer here, Melinda. So Robert, thank you. I will add your email and phone number to the list. So cool. Looks like I did get a comment from Bill to me. He's concerned about the Max Brewer Causeway and if it could potentially fail in a few years. He said the road is in danger of collapsing. And they tend to, according to Bill, they restore it with turf grass and rocks. And he's seen 4 failures since 2010, and it has to be restored frequently, but fails with each major storm. Could you comment on that, Melinda?
I am going to add it's 1 o'clock. So I know our speakers do need to leave at 1 o'clock. So I just wanted to make a time check.
Oh, okay.
I'll say real fast. Yes, Bill, I definitely agree with you that there's some major issues happening at Max Brewer Causeway. And it was one of the locations when we did the Titusville stuff that came out as high priority, just due to the fact that there's infrastructure plus basically no natural, stuff left at that area. So erosion is a problem. I know there's a lot of interest in doing something there, but as far as I know, it has become a little bit controversial. So there's been some slowing down of progress as they try to figure out what is the best method.
Okay, great. Thanks, Melinda. Well, I think we're at time. So I wanted to thank everybody for joining us, and thank you, Kelly and Melinda, for a great talk. And watch for the webinar to be posted on our YouTube channel, which I had the link posted earlier in the chat. So anyway.